Hello, welcome to class number 11 in thermodynamics. We're going to introduce enthalpy and specific heat today. So this is one of my favorite topics, that enthalpy. All right, so I'm using a new microphone. It's new. I've actually owned it for a while. I need to get the little add-on thing that gets rid of this volume thing that's stuck over here in the corner. So anyway, this is section 3.9, but maybe you can't see it. I think you can't see it because of this stupid volume thing. Anyway, so this is section 3.9, the thermodynamic property enthalpy, which is capital H for the entire enthalpy, or lowercase h for enthalpy per mass. So the Wikipedia definition. Enthalpy is the sum of the system's internal energy and the product of its pressure and volume. So it's actually, from what it says here, it's actually sort of like not a new thermodynamic property, but it's a convenient thermodynamic property that merges together internal energy, which we've already been using, and pressure and volume. Sometimes we call this flow work. Here's flow work right here. And so it's a forever convenience, and it kind of can replace in many things. So you could kind of think of internal energy as being more relevant when we have a single thing, a single quantity of mass, and internal energy is about the molecules that are excited inside that internal mass. And then we do work upon that mass, so we don't need to separate the two things out. But sometimes when we have more flow work that's taking place, enthalpy is a better choice to completely capture the state of the energy in the flow. So remember that we're looking at state properties as opposed to transient properties. I want to be careful of the transient because it's usually time. So maybe I don't want to use the word transient for heat and work, but heat and work are between two states, right? And so that's what takes place between the two states, but the enthalpy is a snapshot at a particular state, just like internal energy was. So that's the kind of the difference that we're talking about. We want to find a state property that fully encapsulates what is happening at an instant with regards to its internal energy and the amount of flow work that you could pinpoint for a particular location. So for a constant process, pressure process, like for instance, where we have this piston and we put a known amount of weight on top of it, and so we have the constant force and a constant area, so we have a constant pressure. And so this is the constant pressure quasi-equilibrium process, and we're putting heat into a gas. That we can write out this basic equation that we have been. And then for the work side of things, and I like marking things up, so let's see if I can find the little pen. Let's see, I'll mark things up. So for this work, as part of that, we can replace it with all of this stuff right here. And so here's the constant pressure that we're talking about process. So we stick that back in there, and we could lump together this internal energy and pressure and times volume and this internal energy. And so that's what we have right here. So we're going to define this grouping as capital H. And then on a per mass basis, we'll go like little u pressure times little v for a specific volume. So there's the introduction of enthalpy and its purpose. And since it's a state property, we can look it up. And not just for steam, or maybe I mean by steam, I don't just mean like the vapor form of water, but like any of the tables that have a phase transition, we can go ahead and look this up. And so for the mixed version of it, we could see, we probably already noticed in the tables, there is an enthalpy entry. And then, so therefore, the only thing we really have left is entropy, by the way, that you've noticed from those tables. And so here you go, here's your H, F and your HFG, right? So this is, and then, refresher, here's your HG. So this is the enthalpy of the entirely gas saturated state. So it's right on the line of the vapor dome. All right. So if you had a particular pressure right here, here is the location of the gas, and then right over here is the location of the fluid right there for the enthalpy. And we'll see that there's graphs of enthalpy versus various things. I think it's usually enthalpy versus entropy is a particular graph called the Molière chart. But we'll see that coming up. So there it is in the saturated steam tables, but we'll also see that we have enthalpy available to us in the superheated. Taking a look at how it changes compared to internal energy is worthwhile. You can kind of sort of track that their enthalpy is always larger than internal energy. Obviously, because it's the internal energy plus something, and that plus something never goes negative. And notice it has the same units as internal energy. Forecasting things to come, entropy does not have the same units. It's on a kilojoules per kilogram degree Kelvin. Okay, so we're going to go into example in the next video. And so we'll be seeing you then.